All right, so let's go ahead and take a look at the mechanical behavior of polymers. So we'll call this part 2. This is chapters 14 and 15 in the Callister text. All right, so we have 3 sort of general behaviors, if you want. We've got our elastomeric behavior, which you can see here in this bottom curve. And so we have a very low elastic modulus. And we're looking at strains now of 100, 2, 3, 400%. This one, this idealized curve they're showing going up to about, almost 800% strain. Recall the metals, we were looking at something like 30% strain for a highly ductile metal. And so this is going to be our elastomer. So this is like your rubber band. So we can pull it relatively easily. When you get it almost fully stretched, it takes a lot more stress as the rubber band chains all the line, and then you get fracture. We can have a ductile type plastic behavior, typically in semicrystalline polymers. You got an elastic modulus in this region. Can't tell from this curve, but this elastic modulus is going to be probably 100 times less than that of a metal. And then we get some yielding here, and then eventually we get fracture. The yielding shows up here as a peak now in the polymers. We no longer have this 0.02% offset rule because the strains are much, much larger. 0.02 is well within the elastic region for a polymer. So for ductile plastics, we can see the yield showing up here as a peak. And then we have our brittle behavior, and we just have the elastic modulus on up until we get fracture. Okay. All right, so let's go ahead and take a look at each of these types. Let's first take a look at the ductile one, because this is similar to what we're used to seeing curve-wise for metal. So when we're looking at the semicrystalline polymer, the idea here is that at this maximum peak here at the beginning, that's where we're getting yielding. And what's happening at the yielding is that we're going to get a little necking going on in the polymer. And here's a neck region shown here in this video. And this neck region then gets pretty strong because the chains you can see here are starting to align themselves in the direction of the tensile axis. And so it's going to take a lot more to stretch these now that you're stretching the chains rather than just sort of uncoiling all the kinks. And so this region is actually pretty strong. And so what we'll continue to do then is just to continue to grow that region as more and more of the polymer aligns, and we basically draw the polymer out. And so this is a drawing process. And then eventually we'll get fracture when the chains all align, and then we start pulling the chains themselves apart. So that's what we see sort of in the semi-crystalline case. I'm going to leave the video for you to watch. I'll put that up in the YouTube channel. This is for the high density polyethylene, and there's the YouTube link for that, so you can see that. A little more detail maybe with the semicrystalline polymer. So the elastic deformation piece is showing the amorphous regions between the two crystals here starting to straighten out and align. Okay, so we're just removing all of this sort of kink region. And then if we continue to pull, once these chains get aligned or they're starting to get stretched themselves due to entanglements, this region then gets fairly strong, and then what we'll see is we'll start to actually pull apart the crystals themselves. And so that'll be sort of our secondary stage, pulling the crystals apart, and then they get aligned, and then we just sort of continue this process as the polymer is drawn out. All right, so that's sort of our plastic polymers. Let's go ahead and look at the elastomer. What's unique about the elastomer? With the elastomer, we have an amorphous polymer, and now though we've got some crosslinks. And so when you pull on this, you will get an alignment as you pull apart these sort of kinked regions. But now due to the crosslinks, the chains themselves can't slide along each other because they're pinned, right? Certain sections are pinned by the crosslinks. And so when you let go of this material and take the stress off, it will ball back up. And it will do that with, again, these specific points tied to each other between the chains. And so that gives it this very long elastic type behavior. Okay? If the chains can slide across each other, then you get the plastic behavior. And then towards the end, when you're doing your final stretch, that's when you're again breaking the chains themselves. And so that is your typical elastomer. You can feel this effect going from a high entropy to a low entropy system, right? You got a lot of disorder here, and you start ordering it. So this is an entropy change. If you take a rubber band and pull it really fast, so that you go from this state to this state, and then put it up to your lip, you'll sense a temperature difference. Your lip is actually a very good temperature gauge, and so you'll feel a temperature difference. So just pull quick, stretch, put it on your lip, and take a look and see what temperature you feel. Did it go up or did it go down? And then from your stretch position, quickly release the stress on it so that it goes back to this state, and put it back on your lip and see what the temperature change is there, right? And these should be opposite effects. So one should cool and one should heat. All right, brittle plastics. So polymers are very sensitive to temperature. So lowering the temperature always creates a brittle polymer. And I have sort of firsthand experience with this. I was trying to make an igloo with my kids one winter. I've got these Sterilite containers around, and I didn't want to go out and buy the nice igloo block ones. Figured I'll just use this. It's about the right size. This is made out of polypropylene, and it got too cold, and as I was using this polymer became brittle, and it just completely cracked on me. So I ended up having to buy this anyway, and this is polyethylene. And if you take a look at the glass transition temperatures, you'll see that the polyethylene one is much, much lower than the polypropylene one. So the polypropylene is more sensitive to temperature drop and actually underwent a ductile to brittle transition, where the polyethylene one you can take down to very, very far negative temperatures, and you won't see this ductile to brittle transition. All right. So here's just an example that for polymethyl methacrylate, PMMA, some contact lenses, hard lenses are made out of this base material. You can see the repeat unit here, the MER. And if you go ahead and take a look at the temperature effect of a tensile test, in this particular case, this PMMA is fairly brittle material to start with. So at room temperature, you can see the stress strain curve. It doesn't have a lot of strain here, maybe 6-7%. Okay. As you heat it up, it becomes that nice plastic polymer. You can see this curve here at 60 degrees C, and this goes out to 130% strain to failure. Okay, so a pretty plastic material. 60 degrees C is not that hot. Right? And then you start getting down towards freezing, 4 degrees C, and you have a very nice, very brittle polymer. And so that's just showing you the effect. So within a 60 degree range here, say 56 degree range, you go from a ductile to a brittle transition. Okay. All right, well, I'm going to leave it there. Keep this video short, and I'll see you next time.